on the polynomiography that he invented and discovered and made beautiful, beautiful pictures. And you can see them online. We talk again on some recent results on polynomials and polynomiography. It's a pleasure to have you all. Reminding you that it's a really pleasure to have you, and please refrain from using any electronic devices. Thank you.
Thank you very much. It's always a pleasure to be at Professor Zollberger's seminars, an honor. Nathan, I have a hard time. How can I?
If the clicker's not working, you can just hit the arrow keys on the keyboard will work.
Okay.
Unless the computer's being done.
Oh, very good.
Right.
Okay, so I like to talk about a number of things. I have lectured many times on polynomiography to different audiences and to undergraduate and graduate students and high school students. And so I see that there are a lot of students, probably undergraduate mostly, and that's great. I have taught RST research and also SAS honors course. So it seems to attract students to this subject, and I like to talk about hopefully 4 different things. The first one, how many real attractive fixed points can a polynomial have? In fact, this result, I had a research student who is a math major, math and CS undergraduate, Terence. So we did this jointly with him. We know that a polynomial has, n roots by the fundamental theorem of algebra, complex polynomial. And we know that a fixed point of a polynomial is also, you can think of it as a root of another polynomial, just changing it by x, and subtracting x from it. And the fixed point of a polynomial is 1, a number, so that p of theta is equal to theta. We say it's attractive if the modulus of the fixed point is less than 1, and repulsive if the modulus is bigger than 1, and indifferent if it's equal to 1. Now, why are these good? I mean, what is good about attractive fixed points? One reason is that you can just think of iterating this polynomial, okay? Zk plus 1, you substitute by p of zk, and you start with a seed and repeat this process. So suppose that p of z is a quadratic polynomial. Then this is what we get for the difference. You can easily write it down. And what is interesting is that what pops out here, I mean, it's a simple algebra, it's a derivative here. So when I talk to, for instance, high school teachers, I've talked to them and I say, ask about what they teach, and we don't do derivatives, as if they have to go to the notion of limits and all that. So look, this just pops out of the equation. What is interesting to see here is that if you choose your zk, or zk close to the root theta, okay, then this is also going to be close to p prime of theta, averaging it over 2. So we see the value of the derivative at that root. And if the modulus is less than 1, this says that when you're close enough, the fixed point iterations converge to that root. So this is not Newton's method. I'm just iterating the polynomial itself. So for a general polynomial of arbitrary degree, we can also do the same business and see that zk plus 1 minus theta is something which, as zk goes to theta, becomes the derivative of the polynomial. And you can see that that's why an attractive fixed point is important. So a natural question arises, can all the fixed points of a complex polynomial be attractive? Why? Because let's say, polynomial roots, when we like to find the roots of the polynomial. So, how many people are familiar with fractals? Okay, I see that almost everybody is. And you probably have seen the iterations of z squared plus c, okay, which lead to the Mandelbrot set and so on. But if you have seen the images, you notice that, or if you have even tried to generate those images yourself, you see that although z squared plus c, this is a quadratic, it has two fixed points. You cannot have both fixed points attractive. One of them, at least, is not going to be attractive. So it's somewhat unusual that, this is not something that the books seem to talk about, despite many books that I've seen on fractals. Here is a theorem that Terence and I have proved. Given distinct complex numbers, so I'm going to try to generate a polynomial with prescribed fixed points and prescribed derivatives at those fixed points, okay? And the question is, how can you generate such a polynomial? And there is a theory of interpolating polynomials that comes handy, but it doesn't give you the formula directly. So this H is in honor of Hermita Hermita mathematician. But we came up with a close formula for this polynomial, and having prescribed roots. And furthermore, from this explicit form, we can show that if all these are, this polynomial will have the property that it interpolates. In other words, the fixed points are 0i for all I, and the derivatives are the prescribed numbers. And from this, we can show that if the modulus of alpha I is less than 1 for all I, then the degree of this polynomial is exactly 2n minus 1. So if you want so many fixed points, the degree goes up. In particular, suppose that P of z is a complex polynomial having attractive fixed points lying on a line. Then its degree must be at least 2n minus 1. So this is our theorem, and it's an inductive proof, and it's not takes a few pages. The formula, as I said, is not just the straightforward applications of that theory. The theorem implies that a polynomial of degree n can have at most n over 2, the ceiling of n over 2. It's just, you can't get more than that. Attractive fixed points, that is. This property is not valid if you look at general polynomials. This is a polynomial of degree n plus 1, and you can show that all the roots of unity are attractive. So the derivative at those points is in modulus less than 1. However, the roots are not forced to be on line. Now the question arises, can all the fixed points of a polynomial be attractive? The answer is no, and the proof is not so easy. The basis of attractions, the set of all points that would converge on the fixed point iteration, each of them must contain a critical point, zero of the derivative. But the zero of the derivative can have at most, it's n minus 1, polynomial of degree n minus 1. So by that it follows that they cannot all be attractive. But I don't know an easy proof of that. We have a conjecture, we have proved it only for 2 and 3, and don't know if it follows from some theory or something. But if you have a polynomial of degree n bigger than 1, at least one of the fixed points, at least one fixed point it must have, that the real part of its multiplier is at least 1. So the real part, not only the modulus is bigger than or equal to 1, but the real part. So we call it a real non-attractive fixed point. Solving cubic equations. How many people know how to solve cubic equations? Yeah, one person. Okay, but you know the formula. Yes. Yes. I mean, the thing is, again, because of polynomiography and talking to, teachers, like I tell them, what do students say? Or they say, our students know how to solve equations, quadratic equations. And I say, what does it mean? What does it mean to solve an equation? If you just know the quadratic formula, for instance, and the answer is square root of 2, you're not giving a solution. Suppose I want to approximate. So you have to go to iterative methods. And high school students know how to learn the quadratic formula, but not necessarily iterative methods. Do they know how to solve? Do high school students know how to solve a cubic equation? If they don't have a code, how can they solve it? The formula is too complicated, but a mathematician told me that high school students know how to solve cubic equation. I honestly have not come across even students in my classes,
Not in the US.
Not.
Maybe in China, in Russia. Maybe in Iran.
Sorry?
Probably in Iran.
No, I don't think so. I mean, I think they're having the same problems, if not as anywhere else. Too many, distractions. Solving a cubic equation has a very rich history. In fact, it's one of those, deep results. And there is a formula called Cardano's formula, okay, which, in fact, takes a cubic equation and then first converts it so that the quadratic term disappears, and then looks for, it substitutes for W, you have all probably seen that, and then you end up getting a quadratic equation, and then we solve this quadratic equation, and then we have to substitute for u cubed and v cubed. It's not easy. I mean, it's not something that you can immediately, it takes some work. So, anyway, even if you have the formula for solutions of a cubic equation, you have to do something. So iterations, if you want to really approximate the solution. So I want to take a detour now. Define basic family. I have talked about this in Professor Rutgers seminars before, so I don't want to say too much about this. But there is I assume that everybody knows Newton's method, yes, for finding roots of polynomials. But it turns out that if you define this complicated looking determinant based on a polynomial and its derivative, you can form so-called iteration function, which is z minus p of z and the ratio of two determinants. So when you think of Newton's method, that's just one of these, corresponds to a very simple case of these when m is 2. This is what I call basic family, and essentially I have a book that explores this family. And you can define fixed point, iterations based on this, fixed point iterations. And this is has order m if the fixed points are simple and so on. And special cases of this are Newton's method when m is 2. The third order is Halley's, credited to astronomer Halley. And this is, even these two have a very rich history. Now the general, there is something I call basic sequence. That is, you take a number a and you substitute it into this formula. So you evaluate polynomial and its derivatives at a, and then you evaluate this. So it's something that it's a sequence that depends on the information at an individual point. And there is a recursive formula for those DMs, the determinants. This is not something that one can speak too quickly. But the thing is that if you look at a polynomial, it has roots, okay? And these roots, you can define something with respect to these roots, the so-called Voronoi region of a root. Voronoi region of a root is the set of all points that are closer to this root than to any other root. And it turns out that this family has the property that if you take, say, a polygon inside, no matter how close it is to the actual Voronoi region, there is some m, so that m0, so that when we take m bigger than or equal to m0, the basin of attraction of Bm will come that close, at least. So these, there is an intrinsic geometry in here. And it has the property that if you pick a w that is in the Voronoi cell of a root, the limit of this sequence converges. So, when you look at roots, they have Voronoi regions, the boundaries, and essentially you can close your eyes and take a point and feed it into this formula and it will converge to a root. The problem is that it may take too many iterations for that to do it.
So as m gets larger, the convergence gets faster?
If you use the individual one, yes, the convergence is faster. But here I'm hopping from one fixed iteration function to another. I go from Newton to Halley to the fourth order to the fifth order, but the point is fixed.
So you know how fast the convergence goes?
No, because the convergence in this case, in fact, is linear as you go. But once you pick an individual m and you start iterating with that, then there is a local convergence that is fast. And this is an image which is based on z cubed minus 1, based on this approach. And you see that there is no fractal involved here. People sometimes, and from the talks that I've given and interactions I've had, sometimes I get the impression that even mathematicians maybe think that when you iterate a method to get a root, you're going to get if you were to look at, the visualization of that, you would get fractal images. So some people may think that, well, polynomial, what does it mean? Is fractal another name for fractal? And the point is that no. I have defined polynomiography as visualization of polynomials via iterative methods, but not necessarily using one. And in fact, now I use it even in a broader sense. And this is based on Newton's method. You may have seen this image. If you take z cubed minus 1, apply Newton's method, and based on what happens to the iterations at each individual pixel, you will get an image, this image, which is fractal in nature. This one is an image of the same polynomial, but using a new approach. In fact, I did this with another student I have, REU, where we combine the ellipsoid method, which is for linear programming or optimization, with this Newton's method. So so I'm going to show you a simple way for solving a cubic. You don't have a computer available that you can use. So if you take a cubic polynomial, say having distinct roots, theta 1, theta 2, theta 3, and distinct critical points. So when you think of a cubic polynomial, there are 3 roots, and I'm assuming that these 3 roots are distinct, they form a triangle, and that the critical points must lie inside. They are not the same. If you take this one, z cubed, like z cubed minus 1, for instance, this will have only one critical point. So I'm saying that solving a cubic equation means what is this? Where are the vertices of this triangle? This is a way of thinking of it. And this theorem says, with that assumption, there exists at least one root, so that when you look at its Voronoi region, you will have a critical point in there. And once you have that critical point, you can give it to this basic sequence and generate that. That is guaranteed to converge. So if you look at a general cubic polynomial, the roots will have this kind of shape, modular rotations or scaling. They will either be this or this shape, the roots. If they are of this shape, this is in the Voronoi region. Again, Voronoi region means the set of all points which are closer to this than to the other two. And we see that this property is satisfied with C2. In this case, well, this one is closer to that than to anything. And in this case, both of them are in Voronoi region of this and that. So what does this give? A way of solving a cubic equation. Okay, then, so you take the derivative of the cubic equation, which gives you a quadratic equation. You solve for that, and we get two critical points, and we feed it into this iterative scheme, where for a polynomial, the cubic polynomial, the sequence that you get is this. And the DMs satisfy this homogeneous linear recurrence relation. So all you have to do is keep plugging in to generate higher DMs into this. And that's the formula for that. I mean, in a way, some people may say, look, cubic equations are, who cares about solving cubic equations? And you may be right, because you are not interested in solving cubic equations. On the other hand, if you look at the history of cubic equations, it's very profound. It has given rise to complex numbers, the discovery of the complex numbers. Big mathematicians, such as Smale, they have looked at, for instance, the performance of Newton's method as applied to cubic equations. Suppose I have a cubic equation, and then you iterate Newton's method, which is z, and applies this P of z over P prime of z. So the fixed point iteration is this. Now you may wonder, so you have this cubic equation, and you pick a particular point, and you iterate this. What happens to that sequence? Will it converge to some root? This, according to Smale, his theory and colleagues, is an undecidable problem. So it's a profound problem, that's what I'm saying, and that's why I got interested in this. So the idea is that, or I want to also give you some of my philosophy in this lecture, especially to students, is that polynomiography or polynomial root finding is not necessarily just about finding the roots, solving the points, that you plug in. There are algorithms, many algorithms out there. But this is like understanding the nature of iterations and maybe relations to other fields. For instance, the geometry here, so-called Voronoi regions. These topics are not usually, taught in maybe undergraduate courses. But they are there. They are intrinsic in solving equations, in polynomials. This is a polynomiography of this polynomial. I picked this polynomial, z cubed minus 2z plus 2. In fact, this is, there are many examples, but this one is due to Smale, mathematician. And you see, there are 4 colors here. 3 of them correspond to the roots, basin of abstractions, and then there's this white area. And God forbid, if you pick a point here, you will never get anywhere. You'll just waste your time. However, when you go to this method that generates the basic sequence, you get this area, this region, you get convergence. Except for when you are on the boundary. The reason these areas are dark is because it needs too many you asked. N could be very large for these, so we just truncate the algorithm and dark color it black. All right, so that's number two. Necessary and sufficient condition for local maximum of polynomial modulus. Suppose you have a polynomial, P of z, complex polynomial, and you look at the modulus of a complex of that polynomial. Of course, if you have a complex number is z x plus I y, the modulus of that is square root of that. And you can, if you have a polynomial, P of z is also a complex number. Z is a complex number. But for any polynomial, P of z is also complex. It has a modulus. Now look at the modulus of this polynomial. The modulus of the polynomial, complex polynomial, will then be a polynomial in two variables, x and y. Okay? So if you were to plot it, you would get a surface in 3 dimensions. And you may wonder, what is the maximum of this modulus over the set of all z whose modulus is less than 1? So we are looking at this region, and we want to unit this, and we want to see what is the maximum of this function over there. Why is this problem interesting? Well, in fact, in the book of Polynomial Inequalities by Bahman and they talk about the importance of polynomial modulus in approximating or finding bounds on the norm with respect to other polynomial with respect to other norms. So it is important. There is something called the maximum modulus principle. I'll tell you about that later. According to that theory, the modulus, the maximum of the modulus, happens when on the unit disk. So it will not be a point inside. You see, it's not necessarily convex or anything like that. So the maximum modulus says that's what it tells us. Now, there is actually one of the, this is a result is someone had in around 2000, where they give a very sort of a divide and conquer kind of an approach, which could be exponential for solving it. I don't want to go over that in any detail. This is a 1999 article where the author talks about this. Okay, let me skip that. Now, maybe, okay. So you have the polynomial P of z, and we have its modulus, which is a function, surface, and let's call. So we look at a point, a particular point of the modulus, and the modulus either, is as a surface, it either is ascending or descending, or what shape will it have, the modulus of the polynomial? There is actually a theorem that I call geometric modulus principle in 2001 in Mathematical Monthly, that maybe I can best describe this in this geometric shape. You have a polynomial, okay, and you want to say suppose you want to find the zeros of this polynomial, okay. Of course, if P of z is 0, the modulus is 0, and the modulus is always bigger than or equal to 0. So you can say that the fundamental theorem says It says that this surface touches, the